Okay, on this video we are going to see the Euler-cauchy differential equations. So the characteristic of this differential equation is that now our coefficients are not constants, they are variable. But variable in like a polynomial, like for example in this case x squared and it goes with the second derivative. And here x to the power of 1 goes with the first derivative, and x or no x with no derivative. So that is the rule for this kind of Euler-cauchy differential equation. So this is second order differential equation, and if this was third order, then it will be something like this. It will be like, let me write a number d, x to the power of 3, and here third derivative of y respect to x. Alright, so again, the rule is the number of derivative is the number of the power here. This is not derivative, it's just any number. Okay, that is the rule. Now, in this course, we are only solving up to second order differential equations. So we are not going to cover this kind of third order differential equations, alright? Okay, now solving this kind of differential equations with variable coefficients is a very hard problem. So this will be the only kind of differential equations we can solve in this course. Alright? Okay, now even though you have here x squared, the differential equation is still linear because y and the derivatives of y, the power is 1. Okay? And here I have a non-homogeneous differential equation. So, because it's still linear differential equation, then my solution, my general solution is still the homogeneous solution plus the particular solution. And the homogeneous solution is when this is equal to 0. Okay? Okay, now, here the story is going to be a little bit different from the previous videos. The solution proposed solution of the homogeneous differential equation is going to be y equal to the power of x to the power of m. So it's no longer the exponential, alright? So forget about the rules we saw in the previous videos where the solution was exponential of mx, okay? So forget about that. We are going to propose that as the solution. And again, just like in the previous method, we are going to find first the homogeneous solution, and then we are going to worry with the particular solution. Okay, so the proposed solution is that this is the proposed solution of the homogeneous differential equation. So the homogeneous differential equation is ax squared second derivative of y respect to x squared plus bx first derivative respect to x plus cy equal to 0. So that is the homogeneous differential equation. So we are going to find only this part first and then the particular. Okay, now, if we propose this to be the homogeneous solution, the solutions, then if we replace in the differential equation, then it should be equal to 0. Okay, so let's do it. The first derivative of this is going to be mx to the power of n minus 1. And the second derivative is going to be this down, is going to be m n minus 1 x to the power of n minus 2. Okay, so now let's replace in the differential equation, and you will see why this is the proposed solution. Replacing in the differential equation, then we will have ax squared times the second derivative, and the second derivative is m n minus 1 x to the power of n minus 2 plus bx times the first derivative mx to the power of n minus 1 plus c, the y, the proposed solution, x to the power of m equal to 0. Now something happens here. You will see this am times n minus 1 and then x to the power of, here we have x squared and here we have minus 2. So the addition, they cancel, so it's going to be only x to the power of m plus bm. Same story here. This is the x to the power of 1 and here we have minus 1, so this is just x to the power of m plus c x to the power of m, and this should be equal to 0. But you can see here the x to the power of m is the same, is repeated, so we can factorize it. So because of this property, this is why for this kind of differential equations, this is the proposed solution, because we can factorize. Okay, now let's do the factorization. So it's going to be a, so let's do the multiplication here. Is going to be am squared and minus am plus bm plus c, and then x to the power of m, and this is supposed to be equal to 0. Okay, now we have two options: either to this equation to be equal to 0, because we have a multiplication here, we have two options: either this is equal to 0, or this is equal to 0, or both, but with one is enough. Okay, now this part cannot be 0, x to the power of m, because if that part is 0, then we don't have a solution. So this part cannot be 0. The only thing that can be 0 is this equation. So what we get is 8m squared plus, I'm going to factorize the m here, is going to be b minus am plus c equal to 0. Okay, so now this is a characteristic equation. Check that it is different from the previous method. So, and this is only for Euler-cauchy differential equation. So this is the characteristic equation. Characteristic equation for Euler-cauchy differential equation. Okay? So this is the one we are going to use to solve this kind of differential equations. Now, let's do one little example. Because if we have again the characteristic equation, then we will have the three cases: real different roots, real repeated roots, and real imaginary roots. So let's see one little example with real and different roots. So I'm going to solve x second derivative, x squared second derivative, minus 2x first derivative, minus 4y equal to 0. Okay, so let's solve this example, and now the characteristic equation is going to be this one. Now you don't have to do this procedure, you can jump directly to the characteristic equation. Therefore, the characteristic equation, so this is the a is equal to 1, this is minus 2, the b, and this is the 4 minus 4, the c. But you have to write here b minus a, so be careful with that. M squared, the a is equal to 1, a, b, and c, plus b minus a, minus 2 minus 1, minus 2 minus 1, and then minus 4 equal to 0. So this becomes m squared minus 3m minus 4 equal to 0. Now, two numbers in which the multiplication is 4 and the addition is minus 3. So that is very easy, m minus 4 and m plus 1. Okay, so that means that my first root is equal to 4 and my second root is equal to minus 1. So the solutions are, therefore, if those are the solutions, then my first solution is exponential of 4x, and my second solution is exponential minus x. And therefore, the homogeneous solution is c1 exponential of 4x plus c2 exponential minus x. And that's it. So, as you can see, it's very easy. Now, I made a mistake on purpose, because this is not the solution. What is the problem here? Okay, because we are very used to have the solutions as exponential, we forget that the solution is actually x to the power of m. So this is wrong. This is not the solution. The solution is like this. The first solution is x to the power of 4 and x to the power minus 1. So the homogeneous solution is going to be c1 x to the power 4 plus c2 x to the power minus 1. And this is the solution of this Euler-cauchy differential equation, but homogeneous. All right. For this example, we didn't have to write to calculate the particular solution, so the homogeneous is enough. Okay. Now, on the next video, we are going to deal with the other two cases. So this is real different cases, and we have to do what is the case for the real and repeated roots. All right. Okay. So see you in the next video.